Okay, here's a question. Various questions about ChatGPT. That still seems to be in the news. We're still doing things with it. The big story there tends to be that ChatGPT is very good at writing stuff, and the stuff might be fact, it might be fiction. There's the sort of great thing that can happen of ChatGPT asking Wolfram Alpha, questions which Wolfram Alpha can then really factually respond to, and that becomes an interesting way to kind of fact enhance what GPT might otherwise be writing about that otherwise might be complete nonsense. But there's a question here: how does ChatGPT work? All right, I can tell you something about that. So first of all, what is ChatGPT? These days it's kind of a website made by an outfit called OpenAI that you can type text into, and you can have a conversation. You can chat with it. You can ask it questions. You can ask it to write essays for you. And it does a remarkably good job of writing very human-sounding essays. I think one of the first tests I did on it was write a persuasive essay, I said, for why wolves are the bluest kinds of animals. I'm not sure what I was thinking of typing that in, but the result was quite interesting because it wrote something that started off by saying people don't usually think wolves are blue, but in fact, there is a species of wolf that lives in the Tibetan plateau that is blue, and its name is this, and its blueness comes from the same mechanism that leads to butterfly wings being different colors and so on. And it went on and on and on for a bunch of paragraphs. And it's been kind of taught to make essays like some high school kids are taught to make them, where there's a paragraph at the end that says, in conclusion, comma, et cetera, et cetera, et cetera. Well, it's the things it wrote sounded really quite convincing. They were convincing enough that I was kind of looking up on the web. Is it actually true? Is there in fact a blue kind of wolf? It was all complete nonsense, but it sounded very convincing, and it had all the right structure to be an essay about blue wolves and so on. How does it work? Well, what fundamentally it's doing is it's making plausible English text. And what it's doing is you give it a prompt, a piece of initial text, and it's trying to continue that text in a plausible way. So if you say something like, at a very minimal level, if it was doing that character by character, in English, if you put a Q, it's followed by a U. If you put a TH, well, there's a good chance it's followed by an E. At the level of letters, we know the statistics, the chances that different letters follow each other in something like English. But now we can generalize that. We can make it bigger. I was just looking, if you look at nouns and adjectives, for example. Oh gosh, I was just doing this and I'm already forgetting the results. But you can say things like, if you look at typical English, you could say AI is. Okay, that's and then what's the word that comes next? Maybe the next word is most commonly very, or or it might just be, an for an interesting technology or something like this. But you can ask the question, what is the typical word that follows AI is blah? And so how do you define typical? Well, there are many words in principle in the grammar of English that could follow, but there are particular words that we humans have typically used when we actually write essays and write text about things. And so, for example, in the case of ChatGPT, it took a crawl of the web. So the web has, I don't know how many it is these days, it's a few tens of billions of pages that are reasonably human written that exist on the web. Not that many billions. There are many more. If you say how many different possible URLs are there are trillions of URLs that get used. But the number of really human written, I've got a lump of text, some human wrote this. The number of pages is not that different from the number of humans. Not that we were all writing one page. Some of us have written a lot of pages, and other people haven't been in the business of writing web pages. But it's tens of billions of pages. that exist on the web. And one of the things, you can crawl the web. You just start from one page and you follow all the links on that page. You follow all the links from that page. And chances are you'll eventually get to sort of all the pages on the web. That's a good guess, at least. And so, for example, there's a thing called Common Crawl, which is a project where people have just have gone and done that crawling and have, visited all these websites and repeatedly do so. You can get that. It's a big lump of stuff. You can download it from various websites. And that is a copy of the text content of the web. It's a little bit more complicated than that, because a typical modern website doesn't just have text on it. It has a bunch of JavaScript and so on it. So I think you typically download things called WARC files, which are some kind of web archive format, and it all has to be unpacked. And you have to decide what you really mean by the text and so on. But let's assume you've got big blobs of text that came from the web. So you've got that. You've also got books. There are maybe some number of tens of millions of books that have been written. There are maybe 5 million books that have been scanned, maybe a little bit more than that now. And you can scan the books, you can do optical character recognition, you can pick out the actual text in them. So that's another big corpus of material that you can feed in. And ChatGPT was trained on Common Crawl plus a bunch of books. And so when it says what word typically follows this, it knows that based on having seen all of those different parts of the web and these books and so on. It's like in those things that humans wrote, what is the typical thing that is the next word? Okay, so that's where it kind of starts. But this whole question about kind of what is a typical piece of English, it's more than just saying, given that I had the word is, or the word, I'm going to have the word cat. What's the word that comes before cat? Might it be black or white? It's more than just word by word kind of statistics of what's happening, more than just the chance of what word follows which other word. It's dealing with things on a larger scale, where it's saying, when we look at this whole flow of this sentence or many sentences together, what is the typical way that we would put these things together to form something which is sort of typical of what you would see out there on the web and so on. And in fact, in ChatGPT, I think in its current form, it's really dealing with things that are length, 2048 tokens. A token is roughly a word, but sometimes there's more than one token per word. But that's the kind of block that it's trying to say, I'm trying to make these things of this length that are typical of what is sort of seen out there on the web. And by the time you've given a prompt, the things that can follow, given that you say, I want to do this and this and this, the things that can follow are things that are determined in many respects by the prompt that you gave. So that's kind of the big picture of what it's trying to do. It's trying to mimic the sort of typical stuff that it's seen that humans have written out there on the web and in books and so on. And it is completely remarkable, as far as I'm concerned, that anything like that is as good at producing sort of interesting essay type text or poetry or whatever else as it is. It's remarkable. It's something that I think is really a big clue in terms of the way that we should think about processes about human thinking and the nature of meaning and text and all this kind of thing. Nobody knew that this was going to work this well. And in fact, sort of the precursors to modern ChatGPT didn't work as nearly this well. Now, there are lots of things. So in terms of how does it actually work, that's the big picture of what it's trying to do. Mechanically, how does it do that? I can tell you something about that. But just to talk a little bit more about sort of the construction of what's going on, when we make an English sentence, we do it according to the grammatical rules that exist in English. Like we might say, what's a good example? My gosh. The crocodile ate what do crocodiles eat? Ate the fish. And then, that is a structure of an English sentence. The crocodile, that's a noun phrase. Ate, that's a verb. The fish, that's another noun phrase. And so we know that English is set up grammatically as something that says that has the form of things like a noun, a subject noun, followed by a verb, followed by an object noun, and so on. That is the grammatical structure. Now, of course, we can have sentences that mean absolutely nothing. We say, the moon, fished the elephant or something. It doesn't mean anything. What does that mean? Or we can have even more meaningless sentences. We can say, I don't know, we can say things where the categories of thing that we put together don't really fit. In addition to things that don't make sense because they're not sort of physically possible, there are also things where the category of thing isn't really right. You could say something like, the house ate the lettuce. Well, houses don't eat things, and it's sort of or you could say the chair was happy. Chairs don't have feelings so far as we know. There are all these ways that sentences can be grammatically correct in terms of their syntax, in terms of the parts of speech and so on, but they're not semantically correct. They don't have meanings that we can immediately identify. Now, if you're writing a poem, it's a little different. A chair could be happy in a poem because poems are a more elaborate, kind of more abstracted form of communication than ordinary text. But this question of what fits semantically together is an interesting question that we really know very little about. And ChatGPT is kind of showing us that there is probably a way of thinking about sort of what fits semantically together, just like there's a way of thinking about what fits syntactically together with parts of speech and nouns and verbs and grammars and so on. And so that there's, I think it's a kind of a very interesting kind of wake-up call for the analysis of kind of how meanings get constructed and how that works. It's interesting that, I've been interested in this stuff for a long time, and I've actually been sort of shocked recently. What's been studied about this, and I've certainly known things that have been studied in the last few hundred years, and I kind of recently realized that most of what's talked about actually goes back to Aristotle from more than 2,000 years ago, talking about kind of the way that you construct things with meaning. And he had a very sort of primitive way of thinking about that. He also had a very different view of kind of how the world is put together and how one could talk about things using science and so on. And it's time for a rewrite, a reboot of that. And that's a project I'm hoping to do fairly soon. But in any case, let's come back to the mechanics of how ChatGPT works. Okay, so it's got text as a prompt. It's trying to continue that text in a statistically reasonable way. Okay, how does it actually do that? Well, the thing it's doing is it's training a neural network to figure out how to do that. Let me explain how that roughly works. So a neural net is kind of modeled on the theory that we've had for the last, kind of 100 years or so about how brains work, that brains have these neurons, and neurons can be either like that they can be active or not active electrically, doing something or not doing something every millisecond, every thousand times a second roughly. Neurons are like, oh, am I going to fire and generate an electrical impulse or not? And a typical neuron might have 1,000 connections to other neurons, little dendrites, little tentacles that sort of stick out in these nerve cells. In our brains, we have maybe 100 billion nerve cells in human brains, and each one might have 1,000 connections to other nerve cells. And so the idea is that when we think, what's happening is that there is electrical activity, one nerve cell, it's kind of spreading its activity to other nerve cells, spreading to other ones, and that's producing this kind of whole pattern of electrical activity in our brains that corresponds to our process of thinking. And we think that memory has to do with the way that there are the connections between nerve cells, the synapses, the connections between the things that stick out of the bodies of the nerve cells, the ways that those can be, whether those connections exist, whether they don't exist, whether they're strong connections, whether they're weak connections. We think that memory and learning has to do with the making of those connections. There are different ideas in detail about how those connections get strengthened and made and what produces that process of learning. And roughly, we have sort of a short-term memory that works for a few minutes, and then gradually over the course of a day or so will form a long-term memory. And there's actual protein synthesis that happens and so on there. There's even very recent theories about how there are kind of dark synapses that have been kind of lying around waiting to be activated, and then sort of come to be active when we form memories and so on. There's some uncertainty about how that all works, but roughly the idea is there are all these nerve cells, all these neurons. They have lots of connections to lots of other nerve cells, and there's something to do with the weights of the connections that encodes the memories. And when we use our brains, what's happening is that neurons activity from one neuron is spreading to others through these kind of connections, through these synapses and so on. And so artificial neural nets are modeled on the same kind of idea, except then instead of being actual nerve cells, there's just things in computer memory, where it's we just have, or in Wolfram language, it's just just some piece of some expression in Wolfram language that represents every one of these nerve cells and represents sort of the value of that nerve cell. And then there are weights by which this nerve cell is kind of how much effect does one nerve cell have on another nerve cell. So you end up with these big, mathematically, it's matrices or tensors, which say, I've got this whole vector of values, this whole sequence of values, and I'm going to determine from that a new sequence of values. And roughly what ends up happening is you add up, you say, this is the input sequence of values. I'm going to take I'm going to weight those values in different ways. I'm going to add them all up. And then there's kind of a thing where, in addition to just adding the numbers up, you have some kind of threshold. The most common thing that's done in current neural nets, a thing called ReLU, which is actually a very simple thing. It's just if the weights where you add up all these numbers can be either positive or negative. If the resulting added up thing is negative, it's 0. Otherwise, it's just the value that you got. That's a simple way to do this sort of thresholding effect. In actual brains, it probably works a bit differently, but that's kind of the basic idea. So the way it works is, in an artificial neural net and probably in an actual neural net in our brains, there are this succession of layers. And you're saying, oh, we give this collection of activity to the first layer, then it does this transformation, it produces a collection of activity for the next layer, keeps on going layer by layer up through the system, and eventually gets to the output. Now, a question is, so then the issue is, well, okay, what should all those weights be that go from the input to the output? And so then you want to construct different kinds of functions that you can compute. So for example, one thing might be on the first layer, you're giving a bunch of values that correspond to pixel values from an image. And what you want is it goes through the network, many layers, 50 layers or something. And out at the end, you should have something where in the output, there's 2,000 possibilities that correspond to sort of a thing with 2,000 possible values. And one of those values, let's say, is going to be big, and most of the others are going to be small. The big, and those 2,000 things, you should say they correspond to 2,000 kinds of objects that might exist in the world: cats and dogs and elephants and chairs and tables and so on. Each one of those things corresponds to one of those objects. And what you want is a process where you give a bunch of pixels in, you go through 50 layers, and then at the end, the last layer has as output something where most of the values are close to 0, except there's a high value for a few things. And it's like, okay, that corresponds to a picture of a cat. So what you're trying to do is you're trying to, in that particular case, for a neural net that's trying to identify images, what you're trying to do is say, it starts off with a bunch of pixel values. Red, green, blue is this for this pixel, 10 million pixel values or a million pixel values or whatever for an image. And then it's like go through these 50 layers, going through all of these things where you've got all these weights and so on. You might have 10 million weights or something, in different, arranged between these different layers. And eventually out at the other end, you're going to get something where you have a sequence of values and where they're mostly zero, except for the ones that correspond to the things that it thought it saw. Okay, so the big question now is, how do you set up all those weights so that the neural net actually behaves this way? And so that is where you have to train the neural net. How do you train the neural net? Well, you might start off by just having completely random weights. And then you feed in an image of a cat, and it says, oh, that's half elephant and half turtle or something. And it's like, oh, that's not right. Okay, how do you improve it? Well, you say, that's not right. That's pretty far away from what is right. There's what's usually called a loss function. It's like, how far away from being right are you? And what you try to do is you say, okay, you're pretty far away from being right. But if you just change those values in this direction, you'd be getting closer to being right. And so then what you have to do is say, this is what we know in the output. You got an elephant and a turtle, but you really just wanted it to be a cat. So that means the elephant and turtle values are big, but you really wanted the cat value to be big. So you can think about that as the numbers for elephant and turtle should get smaller, the numbers for cat should get bigger. That provides you kind of a way to say, these are the way I should change the numbers in the output. So now the question is, well, how do you change the weights in the inside of the neural net to get you closer to the numbers that you want in the output? Okay, so this is a giant application of calculus. And it's sort of interesting because there are many things in the world where sort of calculus became less and less useful and gave way to a lot of things that were much more about programs and so on. This is one place where calculus is still really useful, because what happens is you're making use of, well, maybe I don't want to go into the technical details of this, but it's in the end, it's making use of the chain rule in calculus, operating on, in calculus, you might study a function of, one variable, two variables, three variables. In neural nets, we're dealing with functions of millions of variables. And what you're trying to do is you're trying to say, okay, you want to back propagate. You want to propagate backwards from the way you want to change the output. What do you want to do to these weights in the middle so that if you were fed that input again, you would be closer to getting the output you want? So what happens is you bash these neural nets really hard. You do, a trillion times. You do this process of saying, hey, what does this input give as output? And oh, that's not quite right. You need to push it in this direction. Let's propagate back from how we needed to push it. Let's get these weights changed in the middle. And you keep doing that. You do it over and over and over again. And eventually the thing learns, in the sense that the weights that are arranged in the middle actually do the thing you want. So the most common form of training, well, in this setup, is so-called supervised training, where you say, here's a picture, it's a cat. Here's a picture, it's a dog. And you do that in typical image identification training. In the early days of this, one used like 25 million images of a total of maybe 5,000 kinds of objects. And so what you do is you keep on saying, oh, here's the picture of a cat. You should say it's a cat. Oh, you're saying it's an elephant. Push in this direction, et cetera, et cetera. So you just keep doing that over and over again. Nobody knew how hard it would be to do this. There's a big discovery in 2011 that it was possible to do this. People didn't know it. It was a month of CPU time. Somebody left something just running. And at the end of it, it turned out it had managed to learn a bunch of things. Nobody knew that was going to work. Nobody knew how hard it would be to sort of bash the neural net to be able to learn these things. But in any case, that worked. And the thing that happens, so there are many, many tricks in how you actually do this training. And, for example, you might not have enough images. You could synthetically make images. You say, well, this is a cat, but we want to add to the cat image something where we just change the pixels around a bit and it's still a cat. And then we use that as another piece of the training. in some places where people are, for example, let's say training self-driving cars to recognize different kinds of objects and so on, there's a certain amount of data you get from just driving cars around or having your fleet of cars from some car manufacturer that's kind of going around and seeing what it sees on the streets and getting all that data back and using that to do more training. But in the end, there might not be enough training data. And in the end, I think what's been done there is people make essentially video games for the cars to drive in artificially. And that's kind of the way that, so they're kind of driving around millions and millions of hours of sort of synthesized experience on roads. And so that, but that's a typical example of kind of this sort of mechanism for training where you say, this is what I want to this is what I'm going to feed in, this is what I want to get out. Now learn in the middle of the neural net to do that. Okay, so in the case of ChatGPT, the thing we want to do is we want to say, here's a piece of English text. It's a big, long piece of, I don't know, you got it off some random web page, or it came from Shakespeare or whatever else it was. It's a piece of English text. Now you say, let me show you, neural net, the first 10 words of that text. And I want the neural net to arrange itself so that it will correctly tell me the 11th word, the 12th word, et cetera, et cetera, et cetera. Okay, so that's the task that you're training the thing on. So what you want to do is kind of bash the neural net. You want to run that enough times with enough different pieces of text and sort of bash the neural net hard enough that it will eventually learn correctly to predict. And you can say to the neural net, oh, you got the wrong word there. Let's poke you in this direction. And then you'll get a different, then you'll get closer to the word you should have got based on the training of the actual text that you're shown. Now, the whole point, the thing that's exciting with something like ChatGPT or with so-called generative AI in general, is that it is often being given inputs that it's never seen before. Let me give the example of a cat and dog identifier first. So let's say you show it a very specific photograph of a cat. Then you could imagine you're going to train it to say, okay, that specific photograph of a cat, it's a cat. But now let's say you modify that cat a bit. The cat has been, I don't know, licking its whiskers or something, or whatever, or the cat has its ear in a different orientation, or the cat is on a different background, or the cat is, put its paw up in some way. You still want to recognize it as a cat. And the big point about these neural nets and so on is that after you've trained it on enough of cat images, it kind of gets the idea of roughly what a cat image is. And so even if the cat had its paw up, it can still say, oh, that's a cat. Okay, so the point with ChatGPT is that it's saying if there's a particular piece of English, then or text, and it could know, yes, that is exactly how it should continue. It's a famous, to be or not to be, that is the question, whether it is nobler and whatever, the Shakespeare speech, right? It could know exactly what the next word is in that Shakespeare speech. But what if you gave it something that it had never seen before? It's gonna try and generate something that is reasonable to generate, but it's never seen that particular input before. And the thing it's going to generate is something that's never been seen before as well. So I will say, by the way, one thing that is important in ChatGPT is that sometimes it's like, I've seen it before. I know exactly how to continue it. Turns out that doesn't produce very good results. So what's done in ChatGPT is it has what's called a temperature, where it knows the most likely way that this is going to continue is blah. But actually, it knows the top 5 ways it might continue. And instead of always picking the most likely way to continue it, it has a little randomness that's sometimes picking the less likely way to continue. And so that's an important piece of the sort of the creativity of something like ChatGPT. I think its parameter is, I think it's set to 0.8. Sort of the I'm certain I'm going to pick the top thing would be 1. So it has a little bit of uncertainty there, and that's important. And if you give it no uncertainty, at least the earlier versions of things like the earlier GPT systems, if you give it no uncertainty, if you say always pick the top choice, it very often gets in a loop, and it'll just keep saying the same thing, the same sequence of words over and over again. The thing that's totally bizarre is that in the end, what ChatGPT is doing is it's adding one word at a time, basically, even just sometimes one token, one piece of a word at a time. And it's producing this essay that seems like, oh, it makes perfect sense. The whole essay makes sense. But yet the way it actually worked was just it's adding one word at a time. And that's really telling us something about sort of the structure of text and things like this. Well, okay, how does it actually do the adding one word at a time? Okay, let's see. There is an idea, things called transformer nets. Okay, so the thing I was telling you about, for example, an image, when you have this image and you've got these sort of artificial neurons and they're connected to other artificial neurons, you're kind of flowing through layer by layer. Typically for an image, the artificial neurons are arranged in kind of an array that corresponds to the geometry, let's say two-dimensional geometry of the image. Those are usually often called convnets, convolutional neural networks, that are arranged in this kind of geometrical way, actually very similar to these cellular automata that I've long studied. But in any case, the way that works is there are these layers of artificial neurons. You go from one to the next and so on. Okay, so there's a slightly different idea that's used when you're generating sequences. When there's as I say, for dealing with images, you start off with your first layers of artificial neurons are arranged in a grid, just like the pixels in the image. Actually, it's very similar to our visual cortex. Our primary visual cortex at the back of our brains also has neurons that are arranged in a way that somehow corresponds to the way that the cells on a retina are arranged in that kind of geometrical structure. Okay, but so when you're generating a sequence, the idea is that you'll have something where essentially the thing you feed into the neural net is something that is going to be, you're trying to add to the sequence. And what you're doing is you're looking back in the previous things that are already in the sequence, and you're taking the things that are already in the sequence, and you're saying, okay, which numbered things in that sequence should I look at to feed into my neural net that works out what the next thing should be? So the typical thing, the so-called attention mechanism, is you're trying to add the next word. So you're going to look back and you're going to say, the word 5 ago, that was important. That was a verb or something. That was important. The verb, the word 15 ago, that was also important. That was some subject of a sentence or something like that. So one of the things you try to do is to learn sort of which word is worth looking at in the kind of preceding part of the text. So that's kind of the attention mechanism. Then what you do is, what you're basically doing is, given a set of words, you're figuring out which words are important, then you're feeding those words into something which is very much the same kind of neural net that I just described, where you're just saying, there's this, you're going to feed it in, and then it's going to produce, okay, I got to explain a couple of other things to make this make sense. Okay, first point is, you are, what starts off is a bunch of words. The cat sat on the mat. Okay, what neural nets deal with are numbers, basically, collections of numbers. And, is it 5.7? Is it 5.8, et cetera, et cetera, et cetera? So how do you turn the cat sat on the mat into a bunch of numbers? So in a first approximation, you just say, okay, the is word number 1, cat is word number 714, sat is word number such and such. You essentially just make up numbers for words. Okay, turns out that the thing that is really useful to do is to make up not just individual numbers for words, but for every word, you have a whole collection of numbers. I think in ChatGPT, it is 16,000 numbers per word. I'm not sure of that order. It used to be maybe 1,000 numbers per word, but these are, okay. So what that is for every word, you're saying, I'm going to characterize this word by saying it's 0.7, 2.2, 4.6, minus 0.8, et cetera, et cetera, et cetera. Thousands of numbers, okay? what do those numbers mean? Well, those numbers are some kind of way of saying what the meaning of the word is. Let me give an example. So let's say you're going to, let's take an example, not with words. Let's say it's with flags of the world or something. You want to arrange the flags of the world on a piece of paper so that flags that are similar looking will be in the same place on the piece of paper. So I don't know, the French flag and the Italian flag, I think they're similar. They'll be in a similar place. I'm doing badly here on my flags, but some country that has a big green flag is really in a different place from the US, which has a red, white, and blue flag, things like this. And the flag of the US flag might be a bit similar to the UK flag. Which one is visually similar to what? So you try and arrange these on a piece of paper according to visual similarity. And so what you can then say is, if you've done that successfully, actually we could forget flags, we could just do letters of the alphabet. So lowercase letters of the alphabet printed, like an A is similar to a G, a V is similar to a Y, things like that. We arrange those in similar places on the page. In Wolfram language, there's a function called feature space plot that does exactly this, that will take a bunch of things and try and arrange them according to their features in some way so that things which have similar features are nearby. Okay, so the result of that is that you can take anything, like it's a V, it's a Y, it's an American flag, whatever it is, and you can place it somewhere in this feature space. And it'll have some coordinate, it'll be at some position. It'll be, X coordinate this, Y coordinate that. And so the point is that you try and arrange it so that the things that are similar in some sense have nearby coordinates. They appear nearby in this feature space plot. Now, in the real case, you're doing that not in 2 dimensions, but in many thousands of dimensions. But anyway, the result is you're trying to get these things where every word is encoded by this array of numbers so that words that have similar meaning are encoded with similar collections of numbers. That's usually called an embedding, word embedding. It's sort of the way that you embed words in, let's say, 1,000-dimensional space. And those embeddings, those learnt embeddings that you deduce from looking at, so the way you learn these embeddings is to, for example, say, this word appears, so words like for colors, for example, might be somewhat nearby in the embedding. And you can tell that because if you look at tons of text, you can substitute red for blue in different places. So there's a sort of a framework for the sentence where could be a red, could be a blue there. We kind of know that those things, red and blue, have to be somewhat similar because they get arranged in the same places in sentences. And so that sort of tells us something about their similarity of meaning. You could swap crocodile for alligator because they appear in similar sentences. And so crocodile and alligator will be near in meaning space. So that's the way that you deduce these embeddings, these mappings from words to collections of 1,000 numbers and so on. Those embeddings are valuable things. That's actually something that people nowadays sell embeddings because what is the good of having an embedding? Well, it means that if you've got a sentence, for example, in the end, you can do these embeddings not just for words, but for sentences. And you say, I want to do a search. I want to find, is there somewhere in my documents where I have a sentence that's like the sentence that I have now? Well, if you could just take every sentence in the document and turn it into this vector of numbers, this collection of numbers, and say, are these numbers close? Then that will tell you, do you have a sentence somewhere in a document that's close to the one that you're looking for? Okay, so there are a bunch of tricks. In the case of ChatGPT, there are a bunch of tricks that are used. So for example, you can say, well, the words come in a sequence, the cat sat on the mat. It's kind of inconvenient to have those words be actually arranged, the cat sat on the mat. Rather, there's a positional encoding so that you basically include with the you include in that big vector, you include information that says, oh, that was the first word, the next one, that was the second word. It's kind of a weird little positional tag that gets included. So that allows you to take all those words and basically put them in a big vat. They're just a bunch of words, bunch of vectors that correspond to these words. Just put them in this vat. Then you use this attention mechanism to decide which of these words you are going to sort of arrange in what order and how much weight you're going to put on each one. Then you feed that into this neural net. Then you get out the sort of prediction for the next word. Now, okay, of course, it's actually more complicated than this. There are like the typical thing that's happening is for every word, you're going through many iterations of this attention feed forward. It's called feed forward when you have this this thing which just sort of feeds through a neural network. You're doing, I think it's 16 layers, maybe it's more than that in ChatGPT. Some number of tens of iterations of that process. Now that's what happens when you're running ChatGPT and it's trying to figure out the next word. When you're training it, you have to do sort of the whole thing kind of in reverse. And you have to kind of feed it. You have to say, well, what do you think? GPT, what do you think the next word is? Oh, no, you're wrong. Let's tell you a different word instead. Okay, so that's the main part of the training is that. There's an additional part of the training, which is tricky and which is actually one of the things that really, I think, has separated ChatGPT from the previous generations of so-called large language models, things which are sort of models of how text is generated. But let me, so the first step is sort of the main training of the thing. So I think in ChatGPT, it's using an underlying language model that has about 175 billion parameters. So over the course of CPU years, GPU years, more to the point, you are sort of gradually refining those 175 billion parameters to represent the statistical characteristics of all of those billions of pages on the web and millions of books and all this kind of thing. Those 175 billion parameters encode the information of what is typical text like that you see out there on the web and so on. Now that's to be compared. In our brains, maybe we have a few trillion synapses between our neurons. So the number of parameters in ChatGPT is not that different from the number in a brain, although it knows about a lot of stuff that is much more obscure than even people like me know about, who have decent human memories. I think and there are a lot of tricky issues about, does it really need precise numbers, 0.2785644, et cetera, et cetera, et cetera. That really doesn't matter. I don't know how many ChatGPT is using, but it's probably just using about 255 levels for each number, rather than having a precise number that can be any number of digits. Okay, so that's the basic thing. Is there's this whole attention mechanism, and it's trying to continue the text. Okay, there's another important piece, which is so-called reinforcement learning applied to ChatGPT. So people ran these chatbots, and it's like, well, what's the chatbot going to produce? Well, sometimes the chatbot produces crazy stuff. It's off yakking about, it's just gone completely bonkers. It's off the deep end in some way. And so what was done was that people were told, have a chat with this chatbot and rate it. Tell it, were you off the deep end? Is it going in the wrong direction? Oh, no, that's great. That's bad. That's great, et cetera, et cetera, et cetera. So groups of people actually did this. And turns out that's a very powerful, it turns out, it's again, not so obvious, that that's a powerful thing for directing what the output will really look like. I think there's probably also a certain amount of templating that's been done for particular kinds of, make a poem, make an essay, things like that. That's sort of just engineering on top of other things, just to make a better user experience for the system. But the thing that is sort of important is that you have these groups of people, and they're like telling it, do this, do that, and that's then fed into this that's fed into the kind of training of the neural net. There's an additional layer that is this reinforcement training that kind of keeps it more or less on track. That seems to be important. People can obviously be very controversial to say, well, you've had some group of people that are training it that are really keen on, I don't know what, the critical character of, why, I don't know, they're really keen on this feature of the world or that feature of the world, or they're really big on promoting the rights of cats over dogs or whatever else it is. And so that set of people that did that final training, independent of just feeding in the big pile of stuff from the web, the people who did the final training have a lot more control over it's going to like cats, not dogs. And so that's sort of an issue, and there's kind of a bunch of questions about how that should be done and what this new generation of kind of AI wranglers, how one sort of gets the right groups of people and how one sort of sculpts things in the right way there. But that's sort of a different issue. But that's the basic idea. So I think I more or less went through kind of how ChatGPT works, and what it's always doing is it's generating a word at a time. Sometimes it's a subword, and you can see that it makes up words because it has tokens that are not quite a whole word. And so it can end up gluing together those two tokens to make up a word that's never been seen before. And so it is, so it's doing this, everything it's doing, it's taking the prompt, the original prompt, it's saying, what's the next token? What's the next word? It's giving you that. It's taking the prompt plus the token, feeding that back as another thing and saying, okay, now continue that. And it keeps doing that over and over again until you get your complete object out. And I think, as I say, it can go about 2048 steps doing that. That's the distance back that its kind of attention system looks to keep coherence in the text. So, if it was talking about blue wolves at the beginning, if you ask it to go too long, it'll be talking about, orange, elephants or something at the end, and it will have completely lost the thread of what it was talking about because it only has sort of a finite look back. That's how far the training could be made to work. It's okay. Well, anyway, so that was a basic explanation.